whenever you want to start.
Thank you, Robert. I want to begin anecdotal. It's the year 2013. Um, I wasn't even halfway through my undergrad studies, and it was a time when it was kind of all about transcending dualisms. My undergrad was in physical anthropology, so that is any material or biological means of observing and measuring human diversity. And I had begun wondering about whether one such means could be neuro and whether that could be, the target locus of my knowledge generation for the future to come. And so one day at the Berlin School of Mind and Brain, during that time, I heard Professor Frisson's talk about the FEP as a candidate language for unifying brain function, and specifically for my intuitions that started forming there to link that to behavior. So this talk, in some sense, is my way of returning to that moment and asking whether we can develop such a language, having realized that it needs to be rich enough to describe multi-scale neurophenomenology in natural or naturalistic interaction. So on the order of milliseconds to minutes, and from subcellular networks up to social coordination. My work in this way also attempts to go back to Francisco Varela's um, goal at naturalizing neurophenomenology. And I try to give it a go by means of geometry and interacting brains. Active inference um, back then in 2013, seemed to provide this generative story about how predictive agents minimize surprise together. And I think what I'm adding here, a good 10 plus years later, is just a tiny sliver, borrowing from geometry, which is an observable. But its relevance within this framework lies in being an added value to how to interpret interbrain connectivity. And also the fact that it's both robust enough for naturalistic settings, yet subtle enough to pick up phase transitions across scales, which we ought to relate for a full account of the phenomenon or domain of phenomena that we call interaction. So, welcome to this talk, everyone, and thanks for having me. I'm Nicolás Hinrichs. I'm working at the Max Planck Institute for Human Cognitive and Brain Sciences in Leipzig and at the Okinawa Institute for Science and Technology. And today I'm going to take you beyond brain synchrony into the realm of geometric hyperscanning under active inference. This talk builds on three interrelated papers by my colleagues and me, and it also draws inspiration from the so-called interactive turn, which in a nutshell argues that being on the same wavelength is a neurobiological reality across neural, behavioral, physiological, and linguistic channels. The first paper there was just presented at the International Workshop of Active Inference recently by my colleague Yuyue. The second one will be presented during NeurIPS, and the last one is still a work in progress, which we aim to submit by the end of the year, and is the actual toolkit to make use of this framework. My goal for today is to show you how coupling active inference with network geometry can give us a new window on dyadic interaction, specifically via affect. So I'll start from general concepts and build up to methods and applications, going from second-person neuroscience and how it relates to active inference, then specifically through affect, and then into the actual geometry and what this special kind of hyperscanning brings to the table in terms of detecting phase transitions, and perhaps an application in shared or collective intelligence research. So, second person neuroscience is the starting point. Most traditional social neuroscience adopts a third person stance, which means that one agent observes and infers the hidden states of another. Second person neuroscience posits that social understanding emerges from real time reciprocal engagement. So the dyad, not the individual, becomes the primary unit of analysis. And interaction itself becomes the medium through which meaning is constituted. So when we talk about second person neural, we're not only talking about two brains, we're talking about coordination across multiple channels, movement, speech, gaze, arousal, which are very underrepresented in current paradigms, like that cartoon tries to show. So the dynamics we're trying to model are inherently both multimodal and multiscalar. Any descriptive language we use, whether geometric, probabilistic, or something else, has to be able to span that richness. To understand how people feel together, we must move beyond detached observation and embrace this dyadic multimodal perspective. Won't bore you too much with this slide because I think you're very well aware of what is active inference. But for maybe the newcomers, active inference is a theoretical framework where each agent maintains an internal generative model of its world and of itself. Agents continually minimize their free energy, prediction error, by updating beliefs and taking actions. For our interests, in social context, each agent's model includes a model of the other agent. We therefore have coupled systems. Each person predicts what the other will do, senses the actual behavior, computes the error, and updates. Our bet is that information geometric tools that build around the notion of curvature entropy, think of it for now as an analog of transfer entropy in information theory, can help us infer the directionality of influence in these loops. And we'll revisit that idea when discussing phase transition and collective intelligence. So again, when two agents interact, their generative models couple, forming a shared generative manifold, which is a state space in which each partner's predictions and states are intertwined. The boundary between self and other becomes fluid and can shift. Each agent's state is entangled with the other's predictions. In this perspective, social coordination is seen as a process of co-constitution across multiple modalities. And then this shared manifold, predictions about the other are not separate from predictions about oneself. Instead, they're integrated into a single dynamic system. For the neuroscientists in the audience, you can think of this as a third brain, perhaps. This perspective dissolves the infinite regress of I model you modeling me modeling you by treating the dyad as a single generative entity. We formalize affect, so specifically valence, as a form of recursive inference. Valence being a continuous appraisal of the integrity of the self model. This has a couple of factors that drive it, namely the magnitude, and so how surprised you are about yourself, and the self-relevance of that error, so how much it matters to your identity. We also include temporal aiming, which controls how far into the past or future your appraisal extends. Here it is important to recognize that emotions are not just raw reactions, they are inferences about self-coherence under uncertainty. And again, emotions are expressed and regulated across multiple channels: neural, behavioral, linguistic, physiological. In a dyad, each agent's emotional coherence is co-constructed by their own predictions and by socially observed information. During a affective rupture, that is a sudden spike in prediction error, a drop in valence is triggered, signaling a breakdown in alignment. Partners can then engage in co-regulation. They adjust their beliefs and actions to reduce prediction errors, gradually recovering. And finally, re-attunement is reached when a new stable alignment is achieved. Both agents start with a high positive valence. In our simulation, experience a sharp drop and then slowly recover as they co-regulate, stabilizing again. This cycle is just echoing what fundamental attachment theory in psychotherapy called rupture repair dynamics or cycles. So part of the motivation for moving to network geometry is similar to the broader push in social coordination research. Many of the tools we've been using are ad hoc and assumption laden. Standard synchrony metrics assume something like a linear stationary relationship between signals. But real social interactions are often nonlinear and context dependent. If you warp one time series nonlinearly, linear correlation can change dramatically even if the underlying behavior is the same. Simple correlation measures just cannot reliably distinguish genuine socially induced coordination from spurious coordination driven by a shared input. And if you don't separate the oscillatory components from the broadband noise in the spectrum, you can mistake shared structure for synchrony. In short, we need an observable that is sensitive to reorganization of the system, but doesn't depend on a specific linear model. Geometry gives us that kind of assumption lean descriptor by focusing on how the interbrain network's shape evolves over time. These limitations become even more acute when we scale to multi-agent systems where shared input and non-linear couplings multiply. So to apply network geometry, we must first construct an interbrain network. Each node corresponds to a cortical region of interest or recording channel, for instance, an EEG electrode, on either participant. An edge represents a weighted connection between nodes, often computed as a synchrony measure, correlation, phase locking, you name it, over a sliding window. The resulting graph includes within brain edges, so the connections within each participant, and cross brain edges, so the connections between participants, and their weights. These networks evolve over time as interaction unfolds. And in principle, we think we could extend this network to include edges representing relationships across modalities. Again, neural, motor, linguistic, or peripheral physiological measures. And then use information theoretic tools to quantify the synergy among them. For now, we'll focus on neural networks, but keep in mind this broader context. Going into a little bit of a primer on curvature and geometry. The Foreman-Ricci curvature is an edge-based measure that tells us whether an edge in a network lies in a redundant cluster or acts as a bridge between separate modules. The formal definition, which I'm displaying a tiny fraction of on the slide, involves node weights and sums over neighboring edges. Intuitively, an edge has a positive curvature when the two nodes it connects share many common neighbors or alternative paths. This indicates a robust redundant connection, whereas an edge has a negative curvature when it is the only link bridging separate communities. This indicates a critical bottleneck or bridge, if you will. These properties allow us to see whether information flows through dense clusters or critical bridges. while the formula may seem a little bit high level or abstract, the graphs here help. It shows an extra edge with high curvature, and the other segments show clusters connected by low curvature single edges. Information theory, as I was saying, has an analogous concept, synergy versus redundancy. In a redundant configuration, multiple channels carry overlapping information. In a synergistic configuration, only by combining channels do we reveal new information. So the FRC, Fuhrman-Ricci curvature. Information theoretic decomposition therefore offer complementary views of network structure. Edges with high curvature live in densely redundant neighborhoods. Information can flow along many alternative paths. So removing one such edge doesn't drastically change the network's connectivity. Whereas edges with low or negative curvature act as unique links. They tie together otherwise separate modules, and changes to them can reorganize the entire network. At each time point, we have a distribution of FRC values across all edges. The curvature entropy is the Shannon entropy of this distribution. Low entropy means the network has a uniform topology. That is, most edges have similar curvature and the structure is stable. Whereas high entropy means the network is heterogeneous. Some edges are clustered, others are bridges, and the structure is reconfiguring. This, of course, depends on the granularity of your time steps. Abrupt changes in curvature entropy are sort of the uh, cherry on top for this type of analysis because they can flag phase transitions in the interbrain network. For example, a spike in entropy might correspond to a moment when the diet experiences an affective rupture and is exploring new coordination patterns. A subsequent drop might correspond to successful repair and re-attunement. To begin validating our method, we firstly have simulated networks with known phase transitions. For example, we start with a regular lattice and gradually rewired edges to create small world of random networks. We've computed curvature entropy at each rewiring probability. I'm showing here the plotted results, showing that curvature entropy remains slow in the ordered lattice and suddenly jumps at a critical rewiring probability. This jump marks a structural phase transition, analogous to an order parameter in physics. Traditional synchrony metrics change smoothly and miss this sharp transition, but curvature entropy captures it. Our geometric marker, like information theoretic surrogates, can detect these reorganization events. As the network rewires and more cross-module shortcuts appear, we see a diversification of edge roles. Some edges become highly redundant, others become unique bridges. Curvature entropy captures that diversification. And at the critical point, the system shifts from a regime where coordination is mostly local and redundant to one where global patterns emerge that can't be reduced to any single module. This is exactly the kind of joint context-dependent structure we care about in social coordination. Synchrony metrics compress complex dynamics into a single value. They can be high even when the underlying network topology is reconfiguring. Geometric measures capture how connections change, not just how much. Are they forming clusters or bridges? They tell us when networks are exploring new structures, something synchrony just cannot reveal. This is why curvature entropy provides a kind of early warning of reorganization and hints at underlying mechanisms. Another way to think about it is to ask what kind of descriptive language do we want for social coordination? A useful language should be agnostic about the low-level signal form, sensitive to nonlinear dependencies, and ideally comparable across modalities. It should apply equally to EEG, FNIRS, fMRI, behavioral networks, even speech-derived connectivity. anything we can cast as a weighted graph, really. Geometric observables like curvature and its entropy satisfy many of these needs. They don't assume a particular waveform or linear model. They just summarize how connectivity is structured and how it restructures over time. So bringing the concepts together, we interpret classic interaction phenomena like rupture, repair, and re-attunement as phase transitions in the coupled system. These phases have multi-level markers, as we were saying already, neural, behavioral, psychological, in the forms of curvature, entropy, and mutual information, gaze, prosody, gestures, and self-reported feelings of connection, respectively. We can think of rupture in particular as a system entering a different coordination regime, a different way of routing information and sharing predictions across brains. Then during repair, the system explores alternative regimes, whereas during re-attunement, it settles into a new stable regime. Last but not least, collective intelligence isn't a simple sum of individual minds. It arises when agents continuously exchange policies, priors, predictions, and control signals. At a certain point, you can no longer understand the system by just looking at the individuals. The supra-individual perspective becomes the simplest description. So to capture this emergence, we propose a metric grounded in information theory, geometric network analysis, and active inference. We'll use the FRC to track how tightly agents' generative models are coupled, and we can quantify when they begin to function as a single system. We will test these tipping points across human-human, human-AI, and AI-AI systems. This is work to come. To summarize, second-person active inference reconceptualizes social cognition as a coupled dyadic process. Emotional valence can be modeled as identity, relevance, or prize, weighted by self-relevance, and blended with the memory of this affect relevance. Geometric hyperscanning, through measures like the former Ricci curvature and its entropy, reveals dynamic phase transitions in interbrain networks that canonic synchrony metrics miss. These phases can be detected and quantified, suggesting the possibility of social markers to guide personalized therapy and developmental research. A richer language for social coordination must be agnostic to signal modalities, sensitive to nonlinear dynamics, and capable of spanning multiple timescales. Geometry offers one such language that sits naturally alongside active inference, giving us a practical, real-time descriptor of social coordination. So circling back to that Berlin conference, active inference gave us a way to talk about brains as predictive, self-organizing systems. And what I've tried to sketch here is how a geometric language for interbrain dynamics can sit alongside that framework as a practical descriptor of social coordination. Ultimately, this geometric approach to interbrain dynamics lays the groundwork for a generative geometry of collective intelligence, where curvature thresholds and tipping points map the emergence of group-level cognition across natural and artificial agents. Thank you so much for your attention. I welcome your questions and ideas for how to take this further.
Thank you, Nicolás. Let's give him a round of applause.
Thank you.
Fantastic talk, very thought-provoking. Now we open the floor for questions from our audience. If anyone has a question, just please raise your hand. Let me change the view so I can see each and every one of you. Perfect. So until people collect their thoughts, maybe I'll venture a few questions I noted down.
Sure.
One is mostly the first one, just clarificatory. When you say that the second person neuroscience framework you introduce that treats the dyad rather than an individual as the unit of analysis, which is in and of itself an interesting move. But when you speak of a shared generative manifold, do you think this manifold is a genuine supra-personal kind of transcending the individual's manifold, or is just as in an ontologically bearing description, or only an epistemic tool to describe two still separable manifolds whose posteriors are still tightly coupled? Because that leads you into the problem of what is the genuine individuation level here, or what is the genuinely individual in this setting, whether the dyad is merely a descriptor or it is itself an individual. And yeah, how do you balance these things?
That's a really good question. Thank you, Robert. I think there's a metaphysical claim smuggled in here for sure. I think as a starting point, to begin modeling this, given that the main sort of quest or the main bottleneck in this is the method itself, to quantify interbrain networks, we've made it a bit easier on ourselves. So the dyad here is described by one coupled generative manifold where the boundary, some other boundary becomes a property of the joint model. So I think there's a way to move past that towards a more complex scenario, especially if we're thinking about multi-agent beyond dyad modeling. But for now, we've kept it as petite as we could.
I see, for sure, as a starting point to
Exactly.
roll on conceptual building. All right. Are there any questions from our audience? Yes, Nick, go ahead. Unmute yourself, please, and go ahead.
Hello, thank you
Hi,
for
Nick.
that very interesting talk. I'm more
Thanks.
just checking my own understanding here, I think, than asking you a question.
Sure.
But the sort of the point at which the joint description becomes more, I don't know, more parsimonious or more useful than the individual descriptions, does this tend to be um, like a steep transition, or is it more gradual?
Mm. That's an interesting question. I think this will depend on firstly, on the experimental paradigm that we're trying to use as a empiric benchmark past the simulation. So in the simulations, you can have both.
Hmm.
I think in the experimental paradigms for now that we're working with to sort of stress test the toolkit, um, I'd say we have both. We have a kind of very binary um, game paradigm where things are, yeah, way sharper, whereas in a VR, 3D augmented virtual sort of haptic paradigm where we use FNIRS, um, there it's way smoother and it sort of builds up uh, with a couple of sort of abrupt spikes here and there. But I would say that will have to develop for sure a kind of convergence zone on which modality delivers what kind of granularity, depending on what kind of time step you're using when you construct your interbrain network itself, right? So in the case of the FNIRS and VR paradigm, your matrix is, of course, by a couple of times bigger than in the EEG case, right? You have a huge vector space of 3D coordinates, both in virtual space and in real space, right? And so timestamping that which already is a headache, but it's also fun. That kind of, I would say, for the time being, and this sort of ground zero of the toolkit, it allows for or enables for smoother tracking, whereas the EEG counterpart just doesn't. Even if you timestamp it more granularly, um, the how much you can zoom in is just limited by that paradigm itself, both the modality and the task that they resolve. So I think that's a really interesting question because it relates to like future to come, as we try to become modality agnostic. There will be a sweet spot across modalities where we hope to see some continuity, right? So as to benchmark how useful it is to track these changes and what ultimately the phase transition looks like in each case. But for now, I would say that's sort of the empiric threshold or the upper bound that we're facing. Yeah.
Can I add a little thing on top? So
Yeah.
might it be possible to use this framework to sort of assess whether an interaction is like properly an interaction right now? So if you were doing some experiment about interaction and you wanted to know, is this a kind of pseudo interaction I'm looking at here? Are these
Mm,
people properly coupled? Um, and then sort of parallel to that, might there be different flavors of interaction where you'd expect to see steep transitions or smooth transitions
right.
as well? And might that be
Right.
useful for classifying tasks and interaction scenarios?
Yeah, no, this is excellent. I think this is even further down the lane when you start classifying the types of interactions after you've benchmarked the method itself, which is where we are at right now, right? If you're thinking, for instance, of a very nuanced and subtle sort of domain of application for this, namely mental health intervention, then you can have all sorts of counterintuitive notions on how the network should behave. Maybe you distrust the person for a second. Maybe you're testing each other. There's dynamics that we just haven't seen in the lab yet in regards to those types of settings or phenomena, where all of these like basic notions just need to be decomposed into more subtle epistemic claims ultimately of what type of interaction they constitute or yeah, what aspect of interaction they amount to. So I think that's an excellent question to keep in mind for a future development of applied versions of this, where a spike in entropy is definitely not sort of definitely doesn't have like a univocal interpretation, um, however specific and embedded in a specific sort of paradigm it might be. It will always depend on yeah, these claims that we'll need to smuggle in, as I was saying before. In the case of therapeutic alliance or intersubjective alliance as a very sort of fragile and intimate case of application, I would say there we definitely need to bring in the big guns of um, psychiatric and psychological evaluation, as well as tools like microphenomenology, etc., um, or dual ethnography to just really have rich descriptors that we can anchor everything else around of.
Thank you very much.
Thanks, Nick.
Thank you, Nick, for your intervention. Stephen, please go ahead.
Thank you. I also would like to probe my understanding.
Sure.
You mentioned a couple of things. One, addressing to neuroscientists, they might think of this coherence as another brain. Is it appropriate to think of this as a spectrum like a single brain can be thought of as multiple brains that are working
Mhm.
together and creating a single coherence. In a single brain, there is a model of the self, a sense of self. And so, following our host's question, your beginning simple conceptualization is looking for when the boundary of the interaction becomes a significant feature. So that's sort of like modeling a sense of self, but you're doing
Mhm.
that. You're the one who is creating that model. Could that be something that is another feature or a variable or a parameter? The self modeling the self, and then looking for that in the interactions, either dyad or multi-agents.
Thanks, Stephen. That's right on point. I think I hadn't thought of this as a spectrum, and that'd be interesting to try to incorporate for sure. For the time being, I had been thinking of this or conceptualizing it as, a state space of otherness, right? Where sometimes it can be mutual, sometimes it can be sort of um, more localized to just one brain, or maybe in another case in time, generalized over the entire network. So I think um, we will need to sort of piggybacking on the previous answer, we probably need to stress test this further so we can see empirically where we can start drawing the line and try to shape this into a meaningful, let's say, representation. But I think a spectrum would be a good way to go about it. So yeah, thank you so much.
Thanks, Stephen. Are there any other questions? Let's see. Maybe until people think more, I can try a second question I noted down here. So looking at your slides, okay,
Hmm.
so you're using the Foreman-Ricci curvature, and the low entropy of this curvature means the network topology is uniform and stable, and with the high entropy, you have a diversity configuring topology, and you model these abrupt changes in curvature as phase transitions. And I think you said in the beginning that they index kind of ruptures. They can be affective ruptures, they can be phenomenologically balanced states, and that can be negative. However, and this is maybe just an example that is a false strawmanning route, but I'm trying to steel man your position. What about changes in network topology that are not accompanied by any type of negative balance? So it will be an increase in the entropy of the Ricci curvature. Let's keep it like that. Like, for example, when you do joint problem solving, when two people work on, they separate to work more on
Yeah.
the problem, or a commando that fights together and then disperses to clear an area, and they don't communicate that much, but they do job, and then they rejoin. So you see a breakdown in network topology, maybe even a transient disappearance of the what you call the shared generative manifold for
Yeah.
a stronger comeback afterwards.
Yeah.
How do you assess this situation?
This is a great point, and I'm happy to say that I'm liaising with a team to attempt to test this with bigger groups that actually resolve tasks within a it's called it something similar to these paintball scenarios, right? Where they're like moving like army like as you were describing. So really looking forward to how that looks, and first and foremost, of course, how feasible that is. Again, thinking of Nurse here as a candidate modality. I think this sort of relates to the previous two questions, and namely, how is it that we're trying to characterize interaction? I think will drive the whole model. So whether we treat a key factor as such or make it just, an aspect in a bigger model. I think that's sort of the question here. And going back to what kind of epistemic claim we're smuggling in, that's sort of the level here that I'm thinking. This method will have to answer such questions in those specific cases, because as you were saying, maybe at some point there is a very neat, global state that you could call, flow between all interacting parties in the group, because they're, solving the task seemingly effortlessly. It might be the case that you just think of this as each brain having its own sort of more granular spikes and drops in different moments of coordination. So I think the full picture will always need to be decomposed into these little details, and the whole average will only tell you so much. I think that's sort of the same case for most measures that we have nowadays. But I think the sort of added value that we have here, or that we're advocating for, is the possibility of zooming in to those in alongside the time axis. So I think in the longer run, having a good dashboard to navigate this intuitively will be also a phase transition in the development of this toolkit, so that you can actually navigate all these brains in their combinations and in the relevant paradigmatic driven selection or portions of connectivity more intuitively, and hopefully won't need to, be constrained by highly technical knowledge to do so. And in that way, I would hope to gather a lot of feedback on how to further refine how it is that these observations can become meaningful at the operational level for such cases that are intuitively more complex because of all the number of interacting elements. Yeah.
Certainly. I mean, it is rational to expect that the moment you scale the number of units that are interacting, you can expect different geometrical regimes to be descriptive of what's going on, and even at a collection of dyads. So the moment you move beyond pairwise interactions, you can, and geometry and certain subtypes of mathematical structures allow you to describe with higher granularity things that might be happening as you scale up, which cannot be recovered from a description at the pairwise unit, like
absolutely
simplicial structures or things like that. So
absolutely. Yeah, I think it goes also the other way around. If you want to take this back to single brain dynamics, can we think of expanding this tool perhaps in the future to, relate to the to the level below the tissue, right? There's this whole I think separation or gap between social neuroscience and network neuroscience, where I think a proper tool might make a good effort to try to liaise those perspectives better, right? I'm not saying, that akin to microtubules or anything of that sort, that there must be a connection that we can observe by means of this, but certainly I would hope that we could bridge that a little bit and take into account the physics of our neural networks in the brain to relate them to what we're describing here.
I see. And maybe one last intervention from my end, and I'm sure Carl will expand on it much more. Have you considered any formal attempts of joining your curvature entropy based formulation with the free energy principle and trying to see whether you can derive in some meaningful way some of your quantities from the VFE, EFE formalism under a specified generative model of dynamic dyadic interaction?
I would need to relay that to our paper, so inviting people to take a look. But happy to say that we're trying to make that a more dense relationship. I think for now it was an attempt to again sort of go back to these intuitions that have been forming and at least from my perspective, just talking for myself, not my co-authors, but around the framework that active inference sort of enables. And I think it's an exploration that will continue with this team for the next year with other types of simulations, other types of hyperscanning data sets. I'm also happy to report. And I think that will require further formulating all of this. But yeah, for the time being, that's the advancement we have.
See, thank you so much.
Thank
And
you.
if there are no other questions from our audience, I suspect it's Carl's turn now.
Is it my turn now?
Yes, high confidence. Fine.
Okay, very good. Wonderful. Okay. I'm just tempted to start with that last issue. But before I do, and Robert usually asks this, how can we help? What kind of feedback or summary or would be most useful? Are you obviously you're writing papers about this, you're starting to submit them. Do you want are you in a position of applying for a proposal, or is it put simply, how can we best critique, summarize, or feedback?
Thank you so much. That's very generous to start with that question of you. Yes, I'm writing some proposals on different fronts. There's the attempt of moving this towards shared intelligence or collective intelligence. There's the attempt of stress testing my kit for as many cases as we can find. And going back to Robert's last remark, there's certainly the interest in trying to continue developing the math of this. As I was saying during the talk, I think we're borrowing from geometry a measure in a nutshell. I think that's the primordial sort of added value that we're putting in place here, and I think its relevance could be further constructed on. So I think in all those fronts, I'd be happy to receive feedback. By all means, yeah.
Okay, very good. Right, so I think practically the addressing the second 2 points of that, which is well, I will paraphrase as lending a formal validation, a construct validation in relation to the free energy principle, for example, in active inference, and also validating the Foreman-Ricci curvature entropy as a useful measure or metric of the phenomena that you're interested in, which is clearly sort of dynamic changes in coupling between people, their rupture and subsequent repair. If I was your mentor or supervisor, what I would do is reframe this notion of stress testing in terms of establishing the validity of the measure. And there are a number of different things, different kinds of validation, but certainly if you're writing a proposal, motivating a particular theoretical or indeed ultimately empirical set of studies or applications of the metric, you would or you could say, I now want to establish the face and construct validity of this measure in relation to a first principle account of self-organization amongst within a dyad or beyond at the sort of collective level. And I'm going to do that by appeal to the free energy principle that underwrites active inference, and particularly
I see.
takes on the free energy principle. And practically, what that would entail is generating synthetic data from a system where you actually know the physics and you know the characterization in terms of dynamical systems theory, and you know the underlying adjacency matrices or graphical descriptions of the interactions. When you've got that, then you will apply your measure. So instead of applying it to lots and lots of empirical and different types of data sets, say sentiment analysis on sort of social network or paintball games, or indeed sort of hyperscanning, before applying it to empirical data, apply it to data that you have generated, where you know the underlying mechanisms and that those mechanisms are consistent with interactive inference or second order inference, or collective behavior of the kind that you would expect to emerge under the free energy principle. You don't have to take notes because this is being recorded, hopefully.
Yeah.
Yeah. So the whole point of me providing a stream of consciousness is you can play this back at twice the speed and just take
Right.
notes. So you can just go for a cup of coffee and let me freak out.
Maybe if I could interject there, we've begun testing this, or as you say, establishing its validity via the small world networks to show the sensitivity to capture phase transitions, and before that also with via the advice of one of our collaborators, Guillaume Dumas, also Kuramoto oscillators, also to prove its sensitivity to phase transitions. I'm wondering what kind of models we could look into beyond that, in regards to the last bit that you mentioned, which is to establish its validity in so far as it's consistent with active inference.
Yeah, well, that's a very good question. And the answer to that is very simple. I think you need to go beyond just loosely coupled Kuramoto or dynamical systems that show some kind of deterministic or stochastic chaos. You need to actually simulate interacting generative models that have that second order aspect. But I'll come back to that at the moment. What I'm saying is that you would be doing simulations a little bit like coupled Kuramoto, phase oscillators, but with the added twist that in fact you can now write this down in terms of Markov blankets and understand the internal dynamics as sense making and also sense making in a joint sense. So you take from the literature random dynamical systems that have been used to simulate communication and dialectic interactions of a formal sort. Now, you could argue that two coupled Lorentz systems of Kuramoto oscillators, are coupled and they are dynamically coupled, and they will show the same kind of mathematical phenomenology that you're interested in. That's not good enough from the point of view of claiming a link to self-organization understood as sense-making or a physics of sense through dyadic interpersonal inference. If you want to talk about collective intelligence, you have to define what you mean by intelligent behavior or sentient behavior. And that means you need to simulate two intelligent inference machines, which means that you need to go slightly beyond the simple mathematical loosely coupled oscillators. Having said that, the phenomena of interest that you will be evincing or aiming towards is something called generalized synchrony or synchronization of chaos. So that's probably when you're talking about using simulations of say phase oscillators, you were probably looking at synchronization, desynchronization events, or trying to simulate them by interfering with control parameters to actually break the generalized synchrony or not. Exactly the same phenomena should emerge if you've actually got two active inference agents in dyadic exchange, trying to infer what the other person is going to generate. So there are a number of these in the literature, and they will be better than, and I say better than the Kuramoto oscillator, simply because the Kuramoto oscillator makes a very strong assumption about the phase reduction. It just collapses everything to a characteristic frequency. You want something that's slightly more realistic, slightly more expressive.
Yeah.
And usually what people do is have compositions of Lorentz systems to simulate this kind of thing. Or Lotka Terra is another chaotic system which is much more apt for describing real biological systems in this way. So there are systems out there. So put this very simply, you take off the shelf, if you can, or you can get a PhD student or a master's student to do it, you take off the shelf simulations of these kinds of dyadic interactions, and then you apply your measures to these to show that they are sensitive to the things that you want it to be sensitive to. And that might entail actually perturbing the simulations of dyadic interactions in a way to induce a rupture and to induce a desynchronization, or change some parameter of the generative models of one or the other agent in order to induce the kind of phase transitions that you're talking about, and then show that, yes, we can pick them up. And furthermore, we can now use formal tools from dynamical systems theory to quantify in conventional terms the rupture in terms of Lyapunov exponents, in terms of all the usual dynamical systems equipment that people would use to make inferences about, say, self-organized criticality. This would be another view of this kind of phenomena. That critical slowing would be another one, another aspect of generalized synchrony. What I'm saying is there are a number of perspectives on this phenomena, and a number of existing measures which can all appeal to different constructs. So when I say construct validity, what I mean is that your Foreman-Ricci construct has to be valid in relation to other constructs. What other ones could you choose? Well, you're going to choose one that has already been established as having a construct validity in relation to dyadic interactions under the free energy principle or under active inference. And that is the only, if you like, that's this, if you like, the I think the most direct and compelling way to establish, on the one hand, the validity of your metric, but also in so doing, you've now formed a deep connection with the active inference and free energy principle literature, where that, or part of the literature which inherits from dynamical systems and the physics of self-organization, not so much the sort of emotional inference or sort of phenomenology part of the literature, but more the biophysics part of the literature. And I think that would address sort of the two aspects of the way that you frame sort of the tripartite ambitions of what's going on here. And then once you've done that, then you can move to predictive validity by then showing that your analysis, your metric, when applied to empirical data, can predict group differences. It can predict a rupture. So that would be the final kind of applicable validity, having established the construct validity, that will be sort of half maths, half numerical studies, but all starting with the phenomena that you're interested in, which is actually two agents in dyadic interaction, not two Rosler attractors or two Kuramoto oscillators, two agents and that sort of brings me to well, the first key point I wanted to sort of bring to the table, and I'll supplement these points by just rehearsing or going through a series of papers, all of which I'm sure you've read, but just to remind me, if I was you, how I would sort of frame a proposal and just work through, or get my PhD student to work through a roadmap to that kind of concept validity. Center stage on this will be the position of the free energy principle, which is that the joint free energy minimizing system between the inside and the outside, or between agent 1 and agent 2, or 2 and 1, is formally or mathematically identical to generalized synchrony. And crucially, synchrony on a synchronization manifold. So what you're looking for is evidence of the dynamics of agent A and agent B tracing themselves out in a joint space on something called a synchronization manifold. And I'll give you a visual example of that before. And that, if you imagine now that synchronization manifold, that is, and this is probably too formal to impress the reviewers of your proposal, but you might be able to frighten them into accepting the veracity of what you're talking about. This synchronization manifold is a statistical manifold. So it has a true information geometry. So we're going beyond just geometry in the loose sense of the actual Ricci curvature, which actually applies to Riemannian geometries. You're in a graph theoretic context, but it inherits from a geometric understanding of metric spaces. Information geometry is a special geometry that applies to movement on a statistical manifold. And that's interesting because if you interpret a statistical manifold in the sense that you are now equipping each point with an associated probability distribution, and you now say that the probability distribution is some kind of Bayesian belief, a conditional probability distribution is some kind of Bayesian belief, you've now got a geometry of beliefs. And that means that the two agents tracing themselves out on this joint space on a synchronization manifold is literally belief updating together. And it has a beautiful maths, and that's called information geometry. You can have information rates and the amount of changing their minds together per unit time, for example. There's lots of really interesting maths. It doesn't sound as though you've gone in that direction at the moment because you've got distracted by FNIRs and people playing paint gun games. But there is a lot of maths and understanding of a formal sort which will allow you to go beyond just geometry and into information geometry on synchronization manifolds. So that's going to be quite a central concept. And the key point here is it's in this joint space of two agents or two systems generally. The free energy minimizing the solution is on the synchronization manifold. So any free energy minimizing system, in your words, now let's stand back and look at the agent and the world, or agent A and agent B, assuming that the agent B is the world for this moment, this paradigm. Then the joint free energy minimizing solution is obtained on and only on the synchronization manifold. And then you can think of your rupture as excursions from the synchronization manifold and the repair as the free energy minimizing process is drawing it back down onto the synchronization manifold. And then you move together dynamically on the synchronization manifold, and then until something awful happens, or there's a particular unstable regime on that manifold that spits you out again. You rupture and then you pull back in again. Now, this phenomena outside the free energy principle and more generally in treatments of generalized synchrony or synchronization of chaos is sometimes referred to as bubbling. So you actually see this in physics and chemistry. You get these ruptures are transient excursions from the synchronization manifold. That exactly in your words, because these are, if you like, departures from a free energy minimizer, they are by definition informationally surprising. So there's some surprising rupture that is then repaired because the whole system is trying to minimize its free energy that lies on the synchronization manifold. So I introduce that because that's something to engage other kinds of theoreticians who might be reviewing your proposals or papers who come at this from a purely maths point of view. And you've talked about rupture and repair, and people in attachment theory may understand what you're talking about. But if you could also say this is just a bubbling event or an excursion from the statistical manifold. And for those people in mathematics, you could also call this a center manifold. That's what he's talking about. A phenomenon known as bubbling and then you can find your favorite reference. So just joining the dots between these different constructs, I think, would be one way of establishing the construct validity of what you're doing. So we're just pursuing that. Well, no, before I do, the other sort of general point I wanted to make was in the proposal and in your subsequent write-ups, I think it might be an idea to differentiate between second order active inference or second order inference and interactive inference. I say that because part of your presentation and certainly the discussions touched upon this issue in an oblique way. To my mind, there's a difference in the scope and the ambition and the kind of modeling and theoretical neurobiology you would need in terms of understanding how I model you. Now that really is sort of an egocentric approach. It's really I'm just interested in how I model myself, and more importantly, how I model you in relation to myself. That's not about the interaction so much. I don't need to worry about you. I just need to know whether you're similar or different, and it's my sense making about you. I think that sort of metacognitive, at the person level, I think that's the heart of second order inference. It's not just
Right.
first person inference, but second person inference and possibly third person inference and so on. That can all be those kinds of questions can all be answered just by looking at one thing and assuming that that thing is the same as the other things it's making inferences about. I think that's slightly different from the joint synchronization and the interactive inference, the inference in the joint space of two individuals, treating the two individuals as now a super individual or a dyad in and of itself, where you're now looking for the synchronization between the two. And I say that just because it would speak to a slightly different literature. You'd be doing theory of mind, you're doing perspective taking, all sorts of things if you went down the second person inference. Whereas you're clearly much more interested in the pragmatics of joint and collective and federated and inference in two or more agents, and how to measure it, how to practically understand the dynamics and how to measure it in different modalities and use it to understand the dynamics of that kind of that kind of coupling. I'm just making that point because if you focus on the free energy principle literature and active inference literature of the second kind, I think you are fully now licensed just to talk about the dynamical systems implication or view of the free energy principle, which is just getting back to the synchronization manifold and minimizing my free energy. You don't need to worry about whether I'm a good model of you or not. Indeed, there are some people, and I'll just try to explain why I think this is important. I did notice that Mao was one of your co-authors and Professor Dumas and the like. So they have a particular interest in the self-modeling, second-person modeling aspect, which in the more sort of generalized synchrony interactive perspective is often downplayed because you have this intersection between sort of you and me and our shared space. That perspective is really taken to the ultimate in the interactive inference picture, in the sense that as if we are exposed to each other for long enough, we will come to share the same generative model, because that's the simplest way of making ourselves mutually predictable. That means that mutually minimizing our joint surprise is to have the same generative model, and that minimizes the joint free energy, and that keeps us on that synchronization manifold. So at which point it becomes our generative model. So I never have to worry about the infinite regress. It's just, if you like, the infinite regress only exists if I model you, modeling me, modeling you, modeling me, modeling you. I don't need to do that if we are really in synchrony, because we have the same generative model. So I don't have my model is your model is my model. I dissolve that regress in a way which I think is a much more plausible mathematical image of interactive inference, not possibly for humans, but certainly for songbirds and insects and the like. They're all equipped with the same generative model, and if they're not, they can learn it from the parents, so that they don't have to worry about what kind of generative model is she using or is he using. We're all using this. We are all together. We're all using the same generative model. It's just now. It is now being or we are conditioning upon that model in terms of sort of joint attention or joint action or a shared agenda, and that keeps us on this synchronization manifold. And the problems occur when it ruptures and your model changes in some way and mine doesn't, or vice versa, and then we have to pair to come back. So I'm just saying, I'm bringing that, it's a subtle point, but it just points you towards one literature and one set of problems as opposed to another literature and another set of problems. And my
Right.
sense is you want to focus on joint attention, joint action, joint synchronization, and this dynamics in the joint space of you and me. It seems that's a much easier, well, not easier, but it's well, actually it is going to be, I think, easier for you to establish constructibility and join the dots with other ways of measuring generalized synchrony in dyadic or multi-agent systems. Oh yes. So practically, from the point of view of this joint synchrony, just to make sure I've understood properly the tenets of your metric. So the Foreman-Ricci curvature is purely a graph theory measure that is based upon the existence of edges in an undirected graph.
Yes.
Yeah. And so
Correct.
you need an adjacency matrix, and it's not a directed adjacency matrix, it's a symmetric adjacency matrix. And then you can, just by counting edges and the like, you can derive from the point of view of this synchronization, and in respect of one of the questions that you were discussing with Robert, it seemed perhaps it's going to be easier if I use the graphics I had in mind just to ask this question.
Sure.
Yeah, let me share the screen, and then I can sort of use my cursor in the fond hope that you can see what's going on here. Right, sorry, yes, just to orientate you. What I wanted to do is just to highlight the work of Michael Breakspear. I don't know if you've come across him, but in the day, 20
Not
years,
yet. Yeah.
well, when you were still at school, if you were doing your based upon your memories of the Berlin Free Energy Principle workshop. So when you were at school, he was Mr. Dynamical Systems, and used to write a whole load of really interesting papers about generalized synchrony and the like, and try how you would understand measures of neuronal dynamics and all kinds of dynamics that ensue from a dynamical systems perspective. But a particularly useful, I mean, this is in itself a useful paper from the point of view of active inference. But what I wanted to pick out was the notion of the synchronization manifold. So here it's in very idealized form. So just imagine a one-dimensional you and a one-dimensional me, or me and you. Then if I sort of think about my state, or something that you can measure, moving around, remembering that state of itself encodes a probability distribution about, for me, you, and for you, me. So it's a belief, which means that this is a statistical manifold. Then what tends to happen in any loosely coupled random dynamical system, or indeed deterministic dynamical system, was noted by Huygens in probably in the 16th, 18th century. This is generalized synchronization of chaos. But technically what it means is that inevitably you and I, if we're just exposed to each other and we're loosely coupled through language, for example, or through me watching your face, or listening to you, then ultimately we will become synchronized, so that you and I both just play out on this synchronization manifold. And I repeat, it is that has the minimum free energy. So you can think of this as a sort of valley where I want to return to. Now, notably, I can walk up and down this, well, my apologies, we can walk up and down this valley, communicating. And of course, if you've got a phase oscillator, then we can't stand still. And as long as your dynamics don't have a fixed point attractor, you will always be moving up and down the synchronization manifold. In this particular example, Michael's talking about riddle basins of attraction, which just basically mean once in a while you will happen upon a particular point on your synchronization manifold that spits you out. And this is the rupture. And then the flow brings you back in again. That would be the repair. And this is, I repeat, a sort of well-known dynamical phenomena in many, many different systems or loosely coupled dynamical systems. The point I wanted to make and then ask you a question. So you've got two kinds of dynamics. You've got lots of stuff going on the synchronization manifold, which is the joint free energy minimizing place to be. And then from time to time, you've got these rupture repair events.
Mhm.
And my question to you is, how would you distinguish between the movement on the manifold and the movement, the rupture repair, which I should mention in the technical literature is called a transverse dynamics. It's at right angles to the synchronization manifold. How would you, and this is a question that you were asked before, how would you use the time-dependent Shannon entropy of the Foreman-Ricci curvature to disambiguate between synchronized joint movement on the synchronization manifold and the transverse rupture repair events? And it strikes me your answer would be easy. Oh, well, it's just I need to focus on the between graph or the between individual edges, not the within individual edges. Is that what you do, or not at this stage? You just lump an entire two-person hyperscanning two people from hyperscaling to one massive graph, and then just take the global Foreman-Ricci curvature, or do you actually identify what it's probably going to have negative curvature, the bridges that keep them synchronized? So how do you is it possible, and do you focus on a subset of edges, or do you just lump everything together?
So both. I think the lumping together is definitely a feature of the toolkit, but the ability of doing time steps of any particular granularity is where the actual added value is at, with the hopes of being able to relate and regress the main signal, the neurophysiological one, against, for instance, behavioral markers. So in this case, I think the synchronized manifold. I think there's some homework here for me to sort of make sense of how a synchronized manifold is represented in neurophysiological terms in this special case, I want to say, of an interbrain network, just because of the very fact that not even going into the transverse dynamics, but thinking just of the brain dynamics in and of themselves, sometimes synchrony is not the sole driver of sort of the explanation of the paradigm, right? It's not solving the entire question for us in terms of what is motivating what. So I think I have to sort of link these two notions of what a synchronized manifold is with what interbrain synchrony is, to have a more meaningful answer or reply for this case. But I would say that because we can timestamp through a sliding window approach both brains, and at the same time this third brain, I would bet on being able to strip away these singular points or tipping points, and not just rely on a grand average, let's say, that sort of has an enslaving framework, right? That would be the actual silver lining behind this effort, and being able to go beyond mere synchrony in time averaged over trials or individuals, but to be able to see a more granular distinction of cycles.
Yes, yes. I mean, don't dissynchrony too much, because generalized synchrony is the phenomenon you're trying to characterize with the
Right.
curve.
Yeah.
Uh,
No, we're inheriting from it for sure. I'm not trying
yeah.
to diss on it.
I know that you mean sort of simple coherence measures don't do it.
Exactly.
Mathematically, when you talk about synchronization, you're talking about something which is slightly more fundamental.
Yeah.
Synchronization. Yeah. Okay. So what you're saying is, if you had a model where you knew the points of rupture and repair, as opposed to the system sitting nicely on its synchronization manifold, you could go in and pick out those time slices where it was in this mode or that mode, and see whether there was any difference or selectivity for the entropy, Shannon entropy of the Forman-Ricci metric. You'll forget this, so but remember it's being recorded. I think one answer to when you've done a bit of background reading or discuss it with some of your more mathematical or technical colleagues, one answer to this is not to use the Shannon entropy of the entire two-person network, but to use a relative entropy of the mutual information between the Ricci curvatures for one brain and the other brain. And that will effectively give you a measure of the synchronization of curvature. And that should be high when you're on the synchronization manifold, but low when you've got these transverse ejections from it. So that might be one way of generalizing the entropy into a relative entropy, where you've now put your knowledge that these electrodes or these FNIR channels came from this person and these ones came from another person, and that puts me in the position now of measuring the within-person curvature, and also now not just looking at the entropy, but the mutual information, the relative entropy of the two. And that may be one way of getting at my question: how do you pick up the shared stuff versus the non-shared rupture dynamics?
Separating the joint withins.
Excellent. Right. So so that was that sort of perspective. I'm just trying to oh yes. So here he was one of your co-authors, wasn't he? Guillaume, in the past?
Yes. He's in the upcoming presentation of I really like this paper, in the toolkit paper, in the actual paper that will introduce the toolkit for this.
Marvelous. I'll give him my best wishes when you see him. He's in Montreal now, isn't he?
Yeah, exactly.
We'll come back to that. I always show this.
Yeah.
Do you know him? Do you?
Yes.
Excellent. Have you collaborated or gone to any of his herb academies?
Not yet. I should reach out. Yeah. My Google Scholar alerts are on for his profile, but no, I haven't reached out yet.
Yeah. He the reason I show this is that again, when you were at school until 2000, I just learned now, 2019, he used to have every autumn a conference that was meant to bring together people interested in synchronization from the point of view of physics and people interested in synchronization in terms of collective behavior. So I remember attending these, and you'd have, Hermann Haken, who was one of the great physicists who developed synergetics of that particular sort in terms of the slaving principle and circular causality and the like. So Herman would talk, and then you get a dance therapist talking from her perspective about how these same dynamics played out in terms of coordination and how that was used therapeutically. And it was a marvelous conference trying to bring together different perspectives, exactly, I think, in the spirit that you're trying to do. But it looks as though they stopped after 20 years, and these are called autumn academies, herb academies. But if he's still if he's still writing this space, I'm sure it'd be worthwhile following him.
Mm.
But it also might be worthwhile just going back and to the documentary evidence of these meetings and just picking
Yeah.
up stuff which speaks to your current agenda. But he'd be very interested in what you're doing. He spent his entire life. He's actually a psychotherapist, but has an enormous passion for the physics of synchronization and joint and dyadic interactions and the like, and how they can be used to measure synchronization. So it's well worth keeping your eye on him. So this is the particular setup. You know, depending upon your aptitude or resources, the software to generate these time series you can download from GitHub or the SPM software, and this is what I meant by off-the-shelf software, and it has exactly the sort of the joint system aspect that you're talking about, and it can now generate data in this joint space of internal, external, or communicative states that you can do bifurcation diagrams on. So you don't have to hand wave about phase transitions. You can actually measure the bifurcations engendered by the coupling as they come into phase, when they can hear each other and when they can't. So here's the synchronization manifold from or one summary of this from these time series. From your point of view, this is an example of effectively a repair. It's a repair where the two generative models start off slightly different, but there's an asymmetry, a symmetry breaking, where one of the generative models has less precision on its parameters. So it's more impressionable. So it's now pulled towards the other one. Mathematically, it's a product system, but more intuitively, it's a sort of teacher-student, master-slave, parent-child kind of relationship. So this would be the reason I put this up is if you wanted an off-the-shelf way of generating data that had at least repair to a synchronization manifold that can be characterized, that is already in the literature. So you don't.
That's great.
That's one kind of validation. All you need to do is to pull out these time series and apply your measures to them. And then you've established a construct validity into something that was already there and already had an established validity. So that was what I meant by meeting aims 2 and 3 with some off-the-shelf established stuff. Have you seen this recently by Peter?
I had not, no.
No, it's just it's not going to affect anything, but it is just an interesting
Cool.
way of looking at something you referred to a couple of times, which is that there may be an emergent kind of inference from the collective that would not be deducible from any given individual. So what Peter did here was sort of ask a slightly tangential question and ask, well, can I, if I have an ensemble of agents who, to a certain extent, some of the internal agents share a generative model, can I identify a Markov blanket of agents? And does the implicit behavior act as if it had its collective generative model?
Right.
This is closer to the second person inference. It's not so much about the synchronization. It's more about levels of interpretation in terms of sort of inference and the implicit belief updating at different scales in a collective. But I thought it was interesting because you mentioned.
Yeah, thank you. This is great.
What was this one? Oh yes, and of course you.
Oh yeah,
I'm sure you've read that one.
yes.
Actually on it. Yeah, and we've done that one. So this is practically probably the most practically possibly an important paper. Have you read this?
No, I hadn't. Looks like I definitely should.
Right. So this wasn't done when you were at school. This was done when you were working hard, probably on a PhD. And unfortunately, the lead theorist on this work actually left academia about a year ago, but she still lectures on data analysis, not FNIRS, but fMRI and EEG courses. So in a nutshell, if you want to go beyond undirected graphs as a way of summarizing coupling amongst the nodes, and the nodes could be brain regions, or they could be people, they could be whatever you want. And you want to move into a physicist's interpretation of causal influence. So we want to actually start with an influence graph as opposed to a directed acyclic graph, not an undirected acyclic graph, a cyclic graph. Then you're now in the game of not using coherence or synchrony or correlations between the nodes, but actually estimating the directed influence, the connectivity of a directed sort. So basically what you're trying to do is to find a way of analyzing particularly your F-nears data I'm thinking of here, because this is actually applied to fMRI hyperscanning, not F-nears to my knowledge. And the idea here is that you want a directed graph. A directed graph, say between the brain regions in subject 1, the brain regions in subject 2, and between the two brain regions. And I'll explain why that's interesting in a moment. And that directed graph has to be basically estimated from the observable data. So this is the problem that is solved by a particular kind of complex system modeling called dynamic causal modeling, which is not structural causal modeling. It's not sort of structural causal modeling in the sense of Pearl, or in terms of mediation analysis or path analysis, or all those related structural equation modeling. All of these are non-dynamical ways of getting the graph. Dynamic causal modeling starts off with an underlying forward model of the directed connectivity, and then tries to estimate and find the directed edges that best accommodate the data. And then what Edda did was say, okay, now I want to think about this in a hyperscanning situation where I believe that there is a generalized synchrony between these two networks that is not trivially accounted for by shared sensory input or stimuli. And how can I measure that? Well, one way is to start to compare models where you're instantaneously linking or compare models with and without connections between the two brain regions. So if your account of the generalized synchrony is, or if what is happening is that there is a synchronization that can be completely conditioned or accounted for by the shared joint input, then you don't need the interbrain edges.
Right.
But if there is something beyond just a mutual enslavement, say, for example, there was turn taking, and either only you or I were actually hearing something at the same time. If there's something beyond that, then that rests upon our inferential dynamics and our beliefs about what I could hear if I could hear the stimulus, then you should be able to see a telepathy as a directed and reciprocal connection between the same brain areas responsible for listening to music, for example, or firing your paintball gun. Provide a better account of the data than without it. And DCM, or dynamic causal modeling, is simply a tool that allows you to compare models with and without directed coupling. So it strikes me that at some point you probably would want to get into this style. Otherwise, you're left in the world, and I hesitate to ask, but my guess is you're sort of creating adjacency matrices just by some arbitrary threshold on some correlation measure, or some transfer entropy, or some coherence measure, depending on the data at hand, which is absolutely fine when you have to do that, because you're going to have to do that if you're doing tweets on social networks, or sort of firing guns, ball guns. But when you're doing the FNIRS data, you're actually in a much better position because you've actually got time series data here. And if you've got time series data about which you know a lot about the dynamics, you're now in a position to use dynamic causal modeling to get your adjacency matrices, which are now directed. So you can ask questions: did it go this way, or did it go that way, or both? And of course, what you're looking for in the generalized synchrony, after a period of repair, is a bidirectional coupling, from mu to me and me to you, which would be another construct validation, but the construct here would be in the context of dynamical coupling as measured by dynamic causal modeling in a hyperscanning context. So I thought, if you don't know about this work, I thought you should spend a weekend reading about it, possibly forgetting about it, but if not, then it would be in principle directly applicable to your FNIRS data. But it will require you to think more carefully about how you deploy the Foreman-Ricci curvature when you've now got a directed influence graph. So it's no longer just a symmetric adjacency matrix. You've got asymmetries, and the edges they're weighted. Of course, you don't have to retain the weights, but you and all the symmetry, you could make it into a symmetric adjacency matrix in the usual way, and then proceed as normal. And as normal, I mean by sort of normal graph theoretic standards. Or you can stay in this slightly more nuanced world of true causality in a dynamical system and see if there's a literature on applying the Foreman-Ricci curvature to a directed cyclic graph. Because that I think we should have more information in it. And in principle, I see no reason why you shouldn't be able to do that. But I'm not an expert in the in the graph theory things. That's it. That's all I had to say.
Thank you so much. This last bit in particular looks amazing. I think that's the crux, or the core sort of a challenge that I have, indeed, to sort of bring the toolkit to full to its full sort of grasp in regards to the subtleties within interbrain connectivity research. So I'll definitely look into that. And yeah, thank you so much for your insight.
Oh, thank you. That was a very entertaining session. Wasn't it, Robert? Do we clap now?
I think so. I was preparing to say that, but apparently you were too eager. Let's give Nicolás a round of applause.
Thank you. Thank you so much.
Carl, is this the first time where you anticipate our dynamic?
It is, yes. I'd amuse myself and you, so that's good.
All right. So thank you, Nicolás, for this wonderful presentation. As soon as Zoom makes available the recording, I will upload it on YouTube and send it to you, so you have it for your own records.
Perfect. Thank you.
And yes, that concludes our meeting, and we thank you once again, and we will see each other for the next TMB meeting next week. Bye, everyone.
Thank you so much. Bye-bye.